The topic today I'm going to present is about minimum time, minimum loss speed control over the induction motor over a time of period and at constant period. Now coming to the slide, minimum time, minimum loss, minimum speed control of induction motor under a field oriented control FOC, exploring the cutting edges advancements in induction motor control, focusing achieving minimal and optimal speed response with minimal energy dissipation through advanced field-oriented control techniques. This presentation derives the innovative methods design enhance motor performance and designing applications from the industrial machinery to electrical drives in vehicles. The challenge balancing speed and efficiency in induction motor. Before going to this, we all know the induction motor is an asynchronous motor where the stator magnetic field RMF will rotate faster than the rotor, uh, which is known to be asynchronous motor. The cost effect now in the slide of this speed balancing efficiency through a real induction motor. How does the speed balancing efficiency affect the induction motor? Ubiquitously, modern industrial applications, electrical drives, uh, and rebootness of the cost efficiency. However, a significant challenging lies in their efficiency, which often culminates the partial loads, leading the considerable energy waste. This issue is practically pronounced in variable speed applications where motors frequently operate outside the peak efficiency zones. The demand of fast dynamic response crucial and task requiring movements through rapid acceleration traditionally conflicts the global minimizing electrical losses achieving the both simultaneous has been a loading standard for engineering quadim. On the right side we can see the 50 Hz 400 volts control over the induction motor through gate and firing techniques. Field oriented control. What is field oriented control? The foundation for field oriented control. Decoupling control FOC, uh, revolved induction motor control by enabling the decoupling of torque and flux. This breakthrough allows for independent control over these fundamental motor parameters, transforming the complex dynamics and AC motor into an manageable DC motor-like behavior. Accurate regulation. The vector control approach uh, facilitates fast and highly accurate regulation for both speed and torque. Motor can be achieved desired operating points with minimal overshoot time oscillations, which is vital for high performance applications where the paramount. The adaptation of standard and high performance variable frequency drives due to the super dynamic response. However, challenges remain the optimizing the minimal energy losses and enhancing dynamic speed tracking further, especially for highly variable loaded conditions. These all come for the highly variable loaded conditions for FOC foundation of precision control over the induction motor. Breakthrough losses minimizing model predictive control. Recent academic advancements, 2025 research across the university, they have addressable loading standing conditions of balancing speed and efficiency. Not required for this. Minimizing total electrical losses. This new MPC system accounts for the minimizes both copper and iron losses for crossing the maximum efficiency primary source of energy dissipation in induction motors by considering these losses predictions and ensure the holistic approach and efficiency where tested conditions may or may not be differ reduced torque ripple and switching frequency beyond efficiency the undesired electromagnetic torque ripple leading smoother operation and less mechanical stress optimizing stator flux reference. A key innovation of algebraic optimization of the stator flux reference is achieved with additional computational cost, making the solution partial for real-time applications, avoiding need for both powerful expensive hardware. 49% of reduced in total electrical losses compared to a classic techniques. The significant improvement ways to sustainable energy saving and enhance the performance of practical scenarios. How does loss minimize MPC works? MPC means model predictive control. Operates through an understanding of induction motor behavior. Through the core employs highly detailed motor modeling, comprehensive incorporates various losses and components, specifically focusing on both iron core and copper losses, winding losses. Model allowing control over accurate representation over the motor energy consumption characteristics under different operating conditions. The modern predictive control have leverages on breakdown of horizon. The each vector represents different way of motor voltage and prediction over the current can be applied, and it is having the different impact of losses and torque output, where the losses and torque output can be varied in different forms of uh, driving cycles. Complementary strategies: voltage and slip optimization, stator voltage amplitude adjustment, adjusting the amplitude of the stator voltage dynamic based load conditions and significantly reduced losses. At light loads, overing the voltage helps the reduce losses, and this strongly dependent on the magnetic flux density, which is proportional to the voltage, and fine tuning prevents over the excitation and unnecessarily energy consumption. Slip frequency optimization, optimizing a slip frequency in difference between the synchronous speed and the actual rotor speed. The other critical stage, be careful about controlling the slip. The motor operate at its most efficient point for any given load directly influences the rotor current and consequently copper losses. Optimum voltage frequency, the key lies independent dependent on the torque requirement motor adapt the copper and core losses, which increases the flux and frequency. Integration and coupling methods, partially having the slight of XC 400 high performance microcontrollers were used in modern processing units. Necessarily parallel operation capabilities of algorithms real time make the control over the induction motors 15 to 50% of control implementation strategy method. Real world impact is on electric vehicles, EVs. For electric vehicles, loss minimizing control directly translate the extended battery life by significantly reducing the energy waste in motors. More and of stored energy is converted into propulsion, thereby increasing range of reducing frequency and charging. Reduced electrical losses is means heat generation within the motor, leading lower thermal stress and component, potentially extending the motor lifespan and reducing maintenance needs. Industrial variable speed drives. The industrial variable speed drives are equally performed through variable drives that pumps, fan, compressors, and operating the cost reduced assumptions. As of now, improvement also contributes to lower carbon frequency, allowing the global sustainability goals. Enhancement of reliability and comfort. Beyond efficiency, the enhancement torque ripple reduction and facility over the control and impact mechanically reliability, smoother motor operating conditions, wear and tear bearings and mechanical components, leading forever breakdown and lower maintenance cost in application of EVs. It also contributes to the quieter, more comfortable driving experience, free from unwanted vibrations and noise. Visualizing the gains as the further torque ripple waveform, these highlight the dramatic improvement in motor smoothness. Before waveform shows considerable fluctuations and having the ripple factors waveforms losing minimized control, presenting such as motor smoother and stable torque output, reducing the mechanical stress. If the mechanical stress is reduced, the ripple factor and the uh, fluctuations may be reduced for total electrical losses slightly. Loss minimizing and modern predictive control reduce up to 49% of reduction method in electrical appliances. Conclusion towards the smarter greener motor drives. efficiency and performance, advanced model controls, predictive controls, and voltage optimization unlocking capabilities, and once demanded in unpatient boundaries in motor control. Future applications, the future applications will be undoubtedly intelligent control strategies over the various sectors, electrical drives, which is uh, following slightly contribution significantly to sustainable energy efforts. Call to action: we must have innovative control methodologies, drive to next generation under various induction motor applications, and having energy loss scenarios. Thank you.